Hey everybody. Our next talk is a Hackaday success story. It takes 3 projects and they found each other through Hackaday, combined forces, and now you are going to get NeonPixels. What happens when you throw core memory, NeonPixels, and MOS 6502s all together? You get, what do you get? Fun. So please join me in welcoming Andy Geppert, Freyermuth, and Anders Nielsen. Sorry, man.
Hey. Hi, everyone. Thanks for joining us. I'm going to hand it off to Pierre here in a moment, but the 3 of us did put together this project, and the demo is sitting right there, and we're going to save that until the end. But first, we're going to walk through each of the 3 projects individually, and then I'll wrap it up with how the projects came together. Here you go.
Hello, I'm Pierre. So I'm here to talk about the project I made a few years ago. But first, I'll introduce myself, who I am. I'm a electronic technician that love the 8 bits, the small microcontroller. So I used to work with them since quite a long time. So let's go through some of my projects. I worked with flip dot displays. I made a matrix that can track cosmic rays. I also used, for example, this very old plasma display. And most of it, I'm a glowing neon enthusiast. So you'll see where I'm going. So what's those small light bulbs, this INS1? They are still relatively cheap because they are just showing a dot, an orange dot. So I could source many of them. They were made by a company, an Ukrainian company, Gazotron. They consume 30 milliwatts, but they are quite dimmer compared to LED. So maybe we should avoid to time multiplex them if you want to use many of them. Then you need around 100 volts to make them light up. And I asked myself, is it a good idea to make a high current power supply DC for 100 volts? Not really. So I kind of start to think and to step up the voltage from 5 volts. And the circuits can be rather tiny, rather simple, because we are not focused on efficiencies or high current. So it was also an opportunity to iterate and instantiate many, many boards, like you can find for NeonPixels, for example. So a small disclaimer, this will not be efficient. I post you really what I had in mind without any other regard. So as I'm used to pick microcontroller, is there a really cheap one with everything I need? So I need a serial module to communicate and with the ability to daisy chain each pixel, and also just generating the signal to switch the MOSFET to boost the voltage. So I tried this with these simple circuits. I was able to reach the 100 volts breakdown voltage for the tubes to light up with this configuration. So I was rather happy. And then to have a control of the brightness of each bulb. The nice thing with the PIC is they have very few logic cells, so I could combine the switching signal with the PWM to have the brightness control. And this project was done in 2020. In France, it was the lockdown was quite hard, so I got bored. So I could build those boards for the 400 bulbs I had at that time. So I soldered everything by hand. Then I designed 8 by 8 matrix block. It can be, of course, driven by a single data clock signal because it's all daisy chain within the matrix. To not have this scanning effect, all the brightnesses, all the data sent to the pixel are latched by a small pause on the transmission line. And then I had to solder all those sockets again. And then that's the result. You can see it at the beginning of this, at the entrance over there. So it's standing for quite some time at my place as a clock, but you can, of course, play Doom on it, as you can see. And does it happen to you as well? You are really focused on your project, and then you realize many people did that also. So here are some examples of neon bulb matrix as well. You have these are the INS ones. And this is a recent article in Hackaday. And those neon bulbs got the attention of a vintage electronic lover. We'll talk about that later. Thank you.
Hello, everyone. I would like to talk a little bit about why I think a 6502 is a great platform for learning embedded systems. I like to call myself a retro computing enthusiast. I like to make circuits, and I like blinking lights. My current day job is managing 1,000 Macs at Aalborg University, Denmark, and I have a small YouTube channel. Over the past couple of years, I have made a 3-cent micro control some LEDs. I have made a Kansas City standard modem for microcontrollers. I have made an RS-232 serial adapter. I've made a super cheap parallel ROM programmer shield, and I've made some pretty cool 6502 single board computers. I also like to play with modern embedded systems, but they come with some downsides too. This is one of the cheaper high-performance STM32H7 dev boards, and it comes with a lot of extreme features. It's got up to 166 GPIO. It's a 32-bit ARM Cortex-M7 core with a double precision FPU and cache. And it's got 2 megabytes of flash and about 1.5 megabytes of RAM. And of course, it comes with a lot of built-in DSP instructions and who knows what. It has 2 16-bit ADCs that can sample at up to 3.6 megasamples per second across up to 24 channels. And it's got a 12-bit ADC. It's got an LCD controller, a JPEG codec, 5 DMA controllers, 4 I2C lines, 5 USARTs, 5 UARTs, 6 SPIs, and of course it has 19 timers. So you might think, so that's easy to get going with, right? When it has all those features, it must be somewhat easy to work with. And if you look up the data sheet, you'll see it only has about 200 and something pages, right? We can just read that in a weekend and we're good to go and we can control all these magical features. Well, yes, the data sheet has the data, but you have to take a look at the reference manual, which is a few more pages. And when you're done with that, you can move on to the documentation for the IDE. And of course, for each and every one of these features, you have about a 50-page app note explaining how to use each peripheral. So for a beginner, that might be a little bit overwhelming. So what I started with, and what a lot of people usually start with, is something a little older and a little bit simpler. Here we have the Atmega 328 in an Arduino Uno, and it has an AVR 8-bit instruction set, 131 instructions, and fancy features like a 2-cycle multiplier. It runs at 16 megahertz. It has 32 kilobytes of flash. It has 1 kilobyte of EEPROM and 2 kilobytes of internal SRAM. It has 3 timers, a single ADC spread across 8 channels, and it's got 23 I/O lines, of which 6 do PWM. That seems a lot more manageable, especially if we look at the block diagram compared to the one from the STM32H7. So if you really, really want to know what's going on, you can take a look at the instruction set manual if you want to take a look at how the instructions are defined. But usually, people skip that part because that's complicated too. But you get most of the things you need from the datasheet for the microcontroller this time. But it doesn't really explain what's behind all those registers and all the things in the datasheet. So what is ROM, what is RAM, what is a register? Because it's written in 2008, it just assumes that you know all these things already. But luckily, we have the Arduino Uno. You can read through that. You can use the Arduino Uno IDE, and you can put things on your microcontroller and get a Blinky sketch running in a few minutes. But I remember the first time I saw direct register manipulation of the 328 on there, and I thought, this is black magic. Where did you get all these numbers? What's going on? What's a register? And why do I have to put special numbers into special addresses to set a timer? So it didn't really explain that even going through the datasheet or going through any of the Arduino examples. So what if I wanted something even simpler? Something you can really understand. So playing with my bigger 6502 boards, I thought, how simple can we make this? And I thought, let's start with a 6502 core. Let's clock it at 1 megahertz just to keep the numbers nice and round. It has, since this is a 6507, it only has an 8 kilobyte address space, and out of which 4 kilobytes for ROM. It has a 6532 Riot RAM IO and timer. Has 128 bytes of internal RAM. It's got 16 I/O because it has 2 output ports, and it has 1 8-bit timer along with a few regulators on the board. It has a button, an LED, and that's it. So over the last 2 years, I've made it do a lot of fun things. I've implemented bitbang I2C and written an SSD 1306 library in 6502 assembly. I've made it act like a serial terminal, and I've had a lot of fun. This, though, is the new and improved 6501 revision 1. It has all of the above, but as you might see, I've upgraded it to USB-C, and it now has its own CH340G USB to serial chip. It generates a few more clocks to work with other systems. It also has a 74HC138 chip to provide extra chip selects. And almost best of all, to me at least, it breaks out all the control signals, which means it's super easy to connect a different chip straight to the 6502 buses off board, like on a breadboard, for instance. So you might ask, so the 6502, which if you don't know, it was in the Apple I and II. It was in most of the Commodores. It's been in the Ataris, 2600, the VCS, the Atari 400 and 800, and so many other systems. So It's 50 years old. It has 56 instructions. It's got an 8-bit data bus, 16-bit address bus. And to understand everything, and I really mean everything about the 6502, the instruction set, and the 6532, you don't need much. Like, you might look at the manual for the hardware and say, well, that's about the same as the Arduino, right? Well, no, because this hardware manual doesn't just go through what the different registers are or how to program it to do a specific task. It actually takes you by the hand and says, this is what a ROM chip is, this is what a RAM chip is, and this is what address decoding is. So by taking this step back to a time when nobody knew what a microprocessor was, we actually get more info and not less. Of course, it helps a little bit if you also read the programming manual, which will not only just provide the instructions, but also give you a few hints as to how you're expected to program this thing. And when you're done with those two documents, the 10-page datasheet for the 6532 is pretty easy to get past. And I'd like to say one of the biggest reasons we had a computer revolution in the late 70s was that the data sheets for these things were not written by lawyers for other lawyers. They were actually written for people. So you could take this data sheet, take this manual, read it, and actually end up with a reasonable idea of what's going on, even if you're not even a technical person. And I think a lot of people forgot about that. So I put together these things and made a super modern and super easy way to try out 6502 programming on a real 6502 in 2025 and upload code via serial. And I can talk about this, and I do so on my YouTube channel, but we have a few more things we'd like to show.
All right, so moving on to the core memory part of this. I don't know, I'm going to assume that no one here has heard of core memory, so I'll start really simplistic. What you're looking at right there is little tiny rings of ferrite around those wires, and each of those rings can store a 1 or a 0. And this was the predominant form of computer memory, RAM, if you will, in all through the 60s. All the computers used it. So I'm kind of a curious person. I like mechanical things. I like electrical things. And often, I kind of wish I could go back in time and like get a mechatronics degree, because that just totally is the essence of what I like to do, where the mechanical and the electronic stuff blend together. So I'm also interested in space and old computer stuff. And one of the really cool things about core memory is this was used in the Apollo guidance computers that took people to the moon and back. So you go to a museum, you hear about this, you see this, it's under a piece of glass, and you can just stare at it. And I wanted to get hands-on with this stuff. So I went looking for a kit, and I found one on Tindy by UC. He made this kit, which is 4 by 8 bits, so 32 bits total of core memory. I bought that, put it together, and then I thought, well, that was fun, but now what do I do with it? So I started experimenting a little bit. In the lower right corner, there's an LED array that is showing you the state of the cores. And then there's also, coming in from the left, is a little pointer, which has got a magnet on the end of it. And I quickly discovered that you could draw in core memory. So that was like, oh, this is interesting. So I took that, got a Adafruit NeoPixel, not NeonPixel display, put together this little prototype, and I took it to I brought it with me going to Maker Faire, and there was a share a hack, just like last night, where I took this out of my little cardboard box and I started showing people, and they were just like, this is the coolest thing we've ever seen, you got to build this, please make more of these. So I'm like, okay, this looks like it could be interesting. I also shared it at a bunch of other places listed there and had a lot of fun doing that, and got a lot of encouragement from this community to move forward with this project. Found out I could get new old stock cores from Bulgaria via eBay, and it turns out these were originally made 3 hours south of here. So my family and I are here all this week on a vacation, and we got to tour the factory where this stuff was made, which was amazing. This is what they look like on the left. That's a core kebab, just a bunch of cores on a needle. And then in the right hand, I'm showing you the cores. They come pre-programmed as zeros. It's fun because this stuff is so tangible, and I like being able to get a hold of it. You actually do in this turns into a kit that I make, where it gives you the opportunity to put this stuff together and weave it together, and I think that's just a ton of fun. The way that it works quickly is you've got a vertical and a horizontal wire through each core. Each core is 1 bit. The diagonal wire is the sensing wire. So you start out by writing to a core by putting half the current through each vertical and horizontal wire that you need, so that the combined current at the intersection of that wire is enough to magnetize that core clockwise or counterclockwise. And you just arbitrarily define that as a 1 or a 0. And then the way that you read what's in that bit is it's called a destructive read. So you write a 1 to it, and if that diagonal wire senses that it changed, it was a 0. And if it didn't change, wait, did I say that right? Okay. If it did change, then you know it was a 0. If it didn't change, it was already a 1. And there'll be a tiny little pulse of like 25 millivolts in that sense wire, and you can detect that. So simplistically, that's how it works. So then after the encouragement from this community, I decided to build a prototype. Got a little help from YouTube, Sean and Chris, and KiCad is awesome. Figured out how to put all that stuff together, built a board, and it didn't work. So that's the fix in the middle there. That's what an OR gate looks like when you hack it on at the end of the project. So then I got it working, and it was a ton of fun to just experiment with them, how they interact with the different cores, where the flux is. The final product is 8 by 8, so that's why it's called Core64. So it's 64 LEDs underneath 64 bits of core memory. I have kits along, or demos along, to show you guys, so you can all get your hands on and come find me afterwards. But they're a lot of fun to play with, and those are just some examples of some demos that I did. Like there's a game of Pong in there, a game of Snake. There's a drawing and an airbrushing application. But it gets even more fun when you combine it with other Hackaday projects. So I found Pierre's project, and this is what you're seeing here on the screen. These, the NeonPixels are it's just amazing to be able to draw in neon with a magnet through core memory. So these are technologies that existed in the 60s, could have been put together back then. And then I wanted to go one step further, because I really wanted it to be powered by a 6502, because it is the 50th anniversary of the 6502 this year, which is pretty amazing. So I started putting together some code. I was using Anders 65 Wino, and there's only 128 bytes of RAM, so I was writing little teeny tiny submodules, and then I'd push it over the serial port, and I'd test it. And then once I got it working, I'd commit it to the ROM. So I'd pull the chip out, burn it to the ROM, put the ROM back in, and then I'd write another little module, and I kept doing that. I got to this point where I had everything together. Oh, and by the way, you can't do a 6502 computer without a breadboard. So there is a breadboard in this demo that I'll be showing you. And then there's a few mistakes and a few bodges and a few hacks. But ended up getting all the bits in the right order, pushing them out. And the real slowdown, the bottleneck, was that 128 bytes of RAM to work with. And it just so happens that I discovered this Pico ROM on Tindy. So you hook up a USB cable to it, and boom, like 1.5 seconds, whatever you want that ROM to be, it is. And that sped up the iteration substantially. So now we have plasma, magnetic fields, and 6502s together. It could have been made 50 years ago, but it wasn't, and I thought I should do it now. Like I said, happy birthday 6502. And there is a demo that I can show you guys in person out here afterwards, and you can come and talk to any of us and ask us questions and find out more at these links. That's our project. There you go. One quick shout out. You can find us where in these core memory things. You can give them a try. And then the Etch-a-Sketch, Etch-SAO sketch. If you haven't heard, we have stickers. My family and I have stickers to add on, so they say Etch-SAO sketch. And Simon up there in the corner is working really hard, thank you, to get the demo code working so that that Etch-a-Sketch can come alive on all of our badges. Thanks for listening.
Thanks very much. Quick announcement before our 5-minute break while we set up. Thea from Eisler is setting up a badge add-on building thing upstairs. They've got a temperature sensor, I think, on it, and some quick connectors on the side.